I fine. It's the interpreter sign pattern. They just don't say it at any point. Why do I need to read it? Are you looking at my GitHub or their GitHub? No, their GitHub. You didn't do us. I didn't change it, but it's there. Yes.
Okay. So we're back in calculus. Calculus. Uh, and we're in the process of the 5 Spock tests. We did comparison, we did limit comparison test. Now we will do a root and a ratio test in that order, and then the condensation test. And then we will see where did it get its name from. Okay, so there is an interesting difference between the root test and the ratio test. When I teach courses, lower ranking courses of mathematics, then there is no real difference between the two because you only take limits. Here we will take a limit of subsequences. We'll take the lim sup and lim inf. And with that, there is a different, an interesting, for me, interesting difference between the two theorems to test. However, usually when we use them, it doesn't matter because we're actually doing limits. But when we study the test, you will see there is a difference. So the root test, given a sequence an of non-negative number, and assume that the lim sup of the square root, not the square, the n root of an is called L. Then if L is larger than 1, then I'll do it into sections. Bullets. If L is larger than 1, then the series is sigma of an diverge. And if L is smaller than 1, then the series converge. So the difference will be that here we take the lim sup in both cases. In the ratio test, we'll take the lim sup for one case and the lim inf for the other. So you see it's rather similar. It's always limit, always larger than 1, smaller than 1. The only difference is that when the ratio test, one of them is lim inf and not lim sup. Why you will see during the proof. Yes.
In this case, lim sup is just taking the limit of like the biggest limit. Like I don't see.
Yeah, what is the biggest limit? So I'll recap that. If a sequence has a limit, then it's both the lim sup and the lim inf. It's the limit of every subsequence. But sequences could be divergent. It has no limit, but they do have a subsequence that goes to 1 and a subsequence that goes to -1. So the lim sup is the largest limit, the biggest limit of a subsequence, and the limit, the smallest one. So saying that the lim sup is L does not tell us a lot about other elements, right? just tell us that if there is another subsequence that has a limit, have some limit, it will be smaller than L. Okay? So proof. First take the first one. Assume L is larger than 1. Then there exists some subsequence A, K, N that tends to L, which is larger than 1. Sorry, not the sequence itself, the root of it. And of
Is it Kn or is it then? Isn't it then? Because K.
N for AN, but I'm taking a subsequence. So I'm changing N to some sequence. It could be just the even, the elements in even places. So A4, the root would be the 4th root of A4. So if it's A2N, here it will be written 2N, right? Wherever I put N, I switch it by Kn. That's composition. Okay. So Kn and the square root, the Kn root of AKN tends to L, which is larger than 0. Then from some point forward, sorry, I'll rephrase. Choose any C, Q is best. Choose any Q between 1 and L. Because L is larger than 1, you can choose a Q between them. Usually the middle, but it really doesn't matter for the proof. Choose any Q. Then from some point forward, the Kn root of AKN would be larger than Q. If the limit of this sequence is L, which is larger than 1, I'll draw it up, maybe it will help. This is due to the definition of limit. This is the limit, this is 1, and this is some element in between. So if the limit is L, from some point forward, all the elements of the sequence will be in the area of L and bigger than Q. Agreed? So if this is bigger than Q, then AKN is bigger than what?
And Q squared.
Q to the power, not squared, Q to the power of Kn. Agreed? But Q is larger than 1. Then where does this leads us? Infinity. To infinity. Therefore, AN could not possibly tend to 0. And therefore, the series diverge. So I hope you're understanding now what's the main idea here. The main idea of both the ratio test and the root test, which we're doing now, is comparison. It's a comparison test. That's what the reason they now it's you can argue whether it's the comparison test, because I just said that the series doesn't go to 0. When it converges, I'll actually use the comparison test. But in any case, I'm making a comparison with this series. And what is this series? What's q to the power of n?
A number of over.
We have a name for it. What's the series of q to the power of n? What sequence is that? The geometric one, yeah. So both the ratio test and the root test has to do with the comparison to the geometric series. And it makes sense. That's why you take the root, because the geometric sequence, the general element, is q to the n. So the root is q. If it's larger than 1, it's divergent. And if it's smaller than 1, then it converges. So one might say, and what happens if it's exactly 1? So the problem is that in order to actually succeed to compare to the geometric sequence, I need this distance between the two. Because L is larger than 1, I could fix a larger than 1 number between them. If L is actually 1, I'm not sure to which side of 1 is it, the sequence, right? It will come from the left to the right. It's a problem. If L equals 1, I can give you example where it diverged and examples where it converged. It could happen both ways. It says it's not comparable to a geometric series. Okay, so like I said, that would be the general theme of both theorems. The differences will be in the proofs and the statement, and you will see why. But the common thing and why I put them together always, because they both do the same, they compare to the geometric series. That's the main thing about that. Question?
Yeah. Basically, this is for any series. You can just grab the A.
Yeah, that's the positive series. Yes. The 5-spoke tests are for any positive series. That's exactly the whole point in life.
I didn't fully understand how we find the lim sub. Its case,
You calculate it.
yes, but
It would be problematic, but usually that's what I said before, it will be regular limits. Because once you have a regular limit, it's equal to the lim sub. Okay, but if an is made from 2 different formulas, to the even numbers this happens, and for the odd indexes something else happens. So you calculate all the sublimits, partial limits, sorry, and find the biggest one. But it could be hard, but it usually doesn't happen.
is there any case you can give that's not too complicated to?
Just what I said. Just put on the even cases one formula, and on the odd cases another one. You take the bigger one of the two. That's it. So it's really not that interesting. It does happen, I think, in calculus too, when you sum up Taylor series and all the powers are even, which means that the odd powers all have 0 coefficients. So that's I think that's the most used, the only use for that, but yes. Yeah.
Can you just go over the body of the proof? Are we doing proof by contradiction here?
No,
We
we
just
said if the
say-
limit is bigger than 1, that basically means that this subsequence
that's
is
something.
bigger than the geometric sequence that tends to infinity. And that's
Right.
enough to say divergent.
We're gonna prove 2 as well, or is this?
Yes.
Oh,
Yes.
okay,
Yes.
right.
Although it's so similar, because
I'm sure.
instead of big, it will be smaller than, and then by the comparison test, okay, it adds an extra step, but it's very similar. And now assume that L is smaller than 1. Choose some Q larger than L but smaller than 1. Okay. And now there is something which is a bit sensitive, so you need to try to focus. Fight your ADHD. So okay.
Different test.
This is the limb soup. It's very, very important. Why? Where are the move here? Okay. Where are the elements? He looks at this screen. Screens. Okay. So this is the limb soup of the sequence. That means that L is the biggest partial limit of any subsequence. What does it mean about the elements of the sequence?
So smaller than Q.
From some point forward, they're all smaller than Q. Why? First of all, would I say that all the elements are smaller than L? No, because they could tend to L from the right. It could even be that all the elements of the sequence are larger than L, but the limit is still L. But they do have all to be smaller than Q from some point forward. Why? If there were infinite numbers larger than Q, then there must be subsequence, converging subsequence, monotone subsequence that has some partial limit which is bigger than Q. So this is why I need this to be the limb soup, because this makes all the elements of the sequence being smaller than Q from some point forward. I'll try to write some of what I said down. And if there were infinite elements larger than Q, then we could take a monotonic subsequence and which will have a limit larger than Q and therefore larger than the limb soup. Contradiction. You can never have a limit larger than the limb soup because the limb soup is the largest limit, right?
Why does it have like the end of something? Only the end.
Well, what?
Ends.
Yes. Ends is not a word. He's right about that.
Ends. But subsequent
Yes.
isn't a word
Yeah,
either.
subsequent. Ends. Okay. So therefore, from some point forward, all elements of the root are smaller than Q, meaning all of them, not a subsequence. So the n root of an is smaller than Q from some point forward. Therefore, an is smaller than Q to the n. But since the geometric series sigma Q to the n converge because Q is smaller than 1, and then by the comparison test, the first one, our series converge. Okay, all it is a comparison to the Qn, and I'm using the lim sup, which is the higher form of this theorem. It would have been a bit shorter if I would just use regular limit, but it would be less powerful of a theorem. But it actually works with the lim sup, not just when the root has an actual limit. So this is the more powerful version of the theorem. Any questions so far? Let's do a quick example before I move on to the ratio test. Example. Go on. Take the series from n equals 1 to infinity of 1 minus 1 over n to the power of n squared. Thomas, that will help you as well. Okay.
They showed the picture of soup.
Soup? Ah, lim soup.
Let me see.
When you enroll, they say, what is your level? Say high school level, academically, mentally, low elementary school. Okay. So we take this series, it's a positive series. This is a positive series, and we can try to apply the 5-spoke tests. We only learn 3 of them, and this is example for the last one. Calculate the limit of the root. So what is the limit of the n root of this? So you'll notice now that I'm not writing lim sup, and I will note you if the limit exists, then the lim mushroom soup is equal to it. What was? In Russia, it was borscht. Yes. Okay. What? In Mother Russia. Ah, in Mother Russia, yes. And if the limit exists, then the lim sup is equal to it. So here we're going to calculate the limit, what is the case in most exercises. What is the n root of this expression? So it's 1 minus 1 over n to the power of n squared over n, right? Because square root is the power of 1 over, which is 1 minus 1 over n to the power of n. Agreed? What is that limit?
E.
Not exactly. It would have been E if it was a plus. So what do we do? And that's like your homework. Thomas showed me before.
We take a minus.
You say it's 1 plus 1 over minus n to the power of minus n. That is E, due to the theorem that we learned. Okay. And you need to fix what you did. So you take it to the power of minus 1. So that is a specific case of wouldn't it be nice, right? And remember that if an is different than 0, yet tends to 0, then 1 plus an to the power of 1 over an is E. So that's the theorem we did mention. Didn't prove it, but I mentioned it and explained a bit. So we use it. We do wouldn't it be nice? We make sure that here is something that tends to 0, and this is its complete or exact inverse. So this whole thing tends to e in the power of -1. In any case, the answer is e to the -1. And what should I check about the limit of the root? What is the question there? Taking you back to the theorem. We found the limit of the root, call it L. In this case, it's e to the -1. So what is the question about it?
You can convert to other graph, yeah.
Is it bigger or smaller than 1?
If it's bigger or smaller than 1. If it's converge or diverge, that's the result. But you ask yourself whether the limit of the root is larger or smaller than 1. By the way, many students get confused with the limit comparison test. There, we didn't care if the limit was bigger or smaller than 1. If it was a finite number, not 0, something in between 0 and infinity, there were BFFs and the comparison worked. But here, you don't compare to anything. You do, but you don't think about it using the exam, using the test. And you calculate the limit of the root, you find it L, and then you ask yourself, is this limit bigger than 1 or smaller than 1? And what is the answer in this case?
Smaller.
Smaller than 1, because it's 1 over e. 1 over e, which is smaller than 1. And what does that says? And therefore,
It converges.
the series converge.
I mean, I don't know if someone remembers. I don't remember seeing these parts there.
Oh, you're still upset about that.
No.
I don't really remember either. I
Yeah,
can't lie.
it's not that problem. I just don't remember seeing it.
I'll make sure. I'm pretty sure I did. Yes, that's why I'm scrolling. But for your sake, your argument's sake, I think I did like that. I said this is a theorem and moved on. I think it's easy to miss.
But we probably didn't do an example of it, as we were saying.
Yeah, exactly. Probably have a low RAM capacity.
Me?
No, all of you. It wasn't personal. It was a general attack.
It wasn't a personal attack, it was a general attack. So short-term memory.
Voila.
Or any, oh, wow.
Yeah, but again, it was just we finished talking about E, and then I say, and no for general, it's not, it doesn't only work for 1 plus 1 over n to the power of n, but in general for every an that goes to 0. And that's it. And next we will talk about subsequent. Okay, so just what I said, I mentioned it, but quite quickly. Okay. It doesn't matter, but because one of the reasons I did it because I figure out I will speak about it a bit more when we get to function, where the same test hold, but same theorem, sorry, hold. But we usually calculate limits more with functions than with series. And sometimes when I go over about it too much in sequences, the student don't know it about functions. Whatever, doesn't really matter. So that's the case here. Any questions so far up till now? So what test will come next?
That's 4 computation.
Comparison, limit comparison. root and ratio. There are two tests with the geometric sequence, root and ratio. These are the two ways. We learned them about sequences, if you remember. I called it the quotient test, but then I saw it's named ratio. It's the same thing. In any case, the ratio test, and you'll see the small difference here, the interesting difference. Given a positive sequence, non-negative sequence, then one, if the lim sup of the ratio an plus 1 over an is smaller than 1, the series, no, it's not enough. The series converge. If the lim sup is smaller than 1, then the series converge. If the underbar, if the lim inf of the ratio is larger than 1, then the series diverge. So it seems rather capricious why 3 times it was lim sup within the 2 tests, right? In the root test, it was both time lim sup, and in the ratio test, it's 1 time lim sup, 1 time lim inf. So it seems weird, but before I'll prove, I'll give you a quick example that I hope would explain to you why it works the way it works. Example before the proof. Say a sequence decrease by a factor of 2 for every 10 times, and then increase by a factor of 10 1 time, and so forth. Meaning it decreases 10 times by a factor of 2, and then increase by a factor of 10. 10 times by a factor of 2, and then increase by a factor of 10. In this case, what would be the ratio? What would be the sequence of the ratio? So half, 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 right? And then 10. Then half, 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 10. Agreed? What is the lim sup of the ratio here?
In the club.
No, sup is the big one.
Yeah, but you can
10.
have 10.
It's 10. There is no question. That's the sequence. The sequence is half, half, 10, half, half, 10, right? The larger limit is 10, the smaller limit is half.
Yeah, but you have the ratios of the first
Mm.
number.
Don't take the ratio of the ratio. This is already the ratio. I didn't write the original sequence, right? I can write it if it helps. The original sequence would be, I think it will help. The original sequence would be, let's say the first element is 1, okay? Then the next half, then
Or
fourth, and until
256. No, let's say 1024.
no, because the first one is 0. So 0 based. By computer science, you should know this. And then you multiply by 10, and you get 1 over
That's just a 10 over 512.
51.2. Yeah, it is. You know what? I agree. It doesn't really matter. Okay. And then 10 over 2 124, and so forth. Agreed? The ratios is half, 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 10, half, 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 10. Okay. So the lim sup of the ratio is 10, because most of the time the ratio is half, but the infinite number of times it's 10. What do you think about the series? It's guesswork at this stage, but will it converge or not?
I think it will diverge.
I think it's a good question, by the way. You're wrong.
Great.
Why are you wrong? I think you see it. The factor of 10 is negligible versus the factor of 512, basically. If you don't think about it as steps, think about all the 10 steps done together. 11 steps. 10 times dividing by 2, 1 time multiplying by 10. So altogether, in the next time, and I'm having a problem with the 0 count myself because the first time we did nothing, right? If it's 10 times after 1, you know what? I think you're correct, Thomas. Because it's not 0 count. We start with 1 by what I described. In my mind, it was 10 elements, then 1, 10 elements, then 1. But well, I said, do it 10 times, then 1. It doesn't really matter at all, but for the sake of being, it's even nicer to look at it like this, and this is 248. In any case, if you think of all these 11 steps put together, then what you do basically is multiply by 10 over 1,000, which is multiplying by a number much smaller than 1. That's what happens. So, but you do have to sum up all these elements. That shouldn't be, I'm not 100% sure, but I'm pretty sure that would be quite low. And it will converge. That's an interesting question as it is, but I'm pretty sure it's converging. But nevertheless, whether it converges or not, I didn't think the example through. What is very important is that the lim sup has nothing to do with it, right? The number 10 here means nothing because it doesn't tell you how many halves do you have here. If instead of 10, I would keep increasing it and say 10 times, 100 times, 1,000 times. If there will be more decreasing than increasing, then the series will definitely converge because the number will be quite small. I think even with my example, it works, but I'm not sure about it. So the number 10 tells us nothing about the series because the in order to know the magnitude of an element, we need to know all of its history or the ratio history. Meaning, in order to know what the product by 10 did, we need to know the element before that. And to know this element, we needed to know that we did half, 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 half. This is different than what happened with the root. With the root, once we knew the n root of an, we directly know the magnitude of an. Because if the root is smaller than q, then an is smaller than q to the n. But if someone tells me that the ratio, the last ratio, the n ratio is 10, the ratio is 10, I don't know the size of the element because it depends on what happened up until now. Okay, so that's the main difference between the ratio test and the root test, and the lim inf here will cover it because it will basically say the ratio was more than 1 from some point forward, always. And this says the ratio is smaller than 1 from some point forward. And then I could do the comparison test. Okay? So instead of a full proof, I've given you the most interesting part of it. I will say explanation of the theorem. Explanation of the theorem, not a full proof. If the lim sup of an if the lim sup of the ratio, is smaller than 1, then from some point forward, the lim sup, oh, not the lim sup, the actual ratio will be smaller than q, which is smaller than 1. And by comparison.
Comparison. SON.
What are you trying to say? A comparison between the
SO? No, yeah, you're right.
By comparison. Yeah.
I thought there was a T there. By comparison, the comparison test. I don't know. I thought that when it's a verb, then it's a bit different. And by
English is worse than Hebrew grammar.
I'm not sure it's worse, but Hebrew I know better.
Hebrew follows structures. Well, that is English, but Hebrew follows more structures.
And by comparison with I think I said it wrong. That's the problem. And by comparison, comparison always. And by comparison with the geometric series, we are done. So how can we? If the ratio is always smaller than q, then by induction, you show that after n steps, you're not larger than q to the n. Right? That's the thing I'm skipping. We're doing with the full proof, but I hope I conveyed the main thing that it must be that the ratio is smaller than q from some point forward. And also similarly, if the lim inf is larger than 1, if the lim in is larger than 1, then from some index forward, and the ratio would be larger than a q larger than 1, and again by comparison to q to the n, and we get that an tends to infinity and the series diverge. Didn't like a game. After and
I got my, yeah, you have them
after
up there again.
and again. Like, oh, I need a comma here as well. Okay, fine. And so why didn't like series here?
Because it, another.
Another comment. He's right. I was hoping you were wrong. Okay.
Blue is always grammar.
Yeah, no, but I wonder what's the grammatic problem here, but fine. Any questions so far?
What happens when the lim sup is
Nothing.
nothing?
That
You know,
and no, but anything other than what is written, you can do nothing with. Whether it's 1, whether the lim inf is larger than 1, no, that's good. Whether the lim inf is smaller than 1, every other possible thing is not a theorem.
right.
And I've shown you before why. I've given you one example. Because if the lim sup, I give you the example that the lim sup was larger than 1. I could do something similar with lim in smaller than 1, doing factor by 10, 10, 10, and then halving it. Obviously, the multiplying by 10 makes it so large that dividing by 2 did nothing. So it's kind of the same. Any questions up until now? So let's look at the following beautiful example. Let's look at this series of n factorial parentheses. So we'll try the ratio test for this positive series. So we calculate the limit of the ratio. Don't forget limiting it. Sometimes students by mistake just take the ratio and show that the ratio is smaller than 1. Ratio smaller than 1, like Thomas said before, says that the sequence is decreasing. That does not promise me that the series is converging. Most sequences of series are decreasing. Doesn't mean that they are decreasing fast enough. That's why we must calculate the limit of the ratio. So we calculate the limit of the ratio, and the limit of, and what is the ratio? We take, so that's what we need to do. I'll write it without the limit at first, because otherwise I will have to write the word limit a lot. I'll just take the ratio, and by then I will do arrow. So what is what is the ratio? What is an plus 1 over an? So an plus 1 is n plus 1 factorial over n plus 1 to the n plus 1. And if you remember, we did that example, this very example, just before we started speaking about E. And instead of dividing, we'll multiply by the inverse. So here it's n to the power of n over n factorial. Agreed? That is equal to n plus 1 factorial over n factorial times n to the n by n plus 1 to the n plus 1, which is equal to, what is n plus 1 factorial over n factorial?
N plus 1.
N plus 1. So it's n plus 1 times n to the power of n over n plus 1 to the power of n plus 1. Great. Which is n to the power of n over n plus 1 to the power of n, which is n over n plus 1 to the power of n, which is 1 over n plus 1 over n to the power of n, which is, see why I didn't want the limit coming with me? 1 plus 1 over n to the power of n. And finally, what is the limit of that expression? 1 over 8. And what can we say about it?
Less than 1.
Less than 1. And the series converge. Any questions so far?
I'm still not sure how I would see this without you telling me what the page.
Yeah. I got
Which step? Yes.
And
Until here.
no, until there it's fine.
Fine.
yeah.
Yeah.
So the next few steps I actually did as well. But the best thing to do, it wouldn't be nice. You add one and subtract one. And then wouldn't have better. Yeah, and I agree that the way I do it is better, but I didn't do it for you yet. I will do it in the future. Yes, Sammy, question?
I was gonna say, is there, because when I went a bit ahead and tried to calculate it, and I ended up splitting up and doing 1
Okay,
minus 1 over n
I'll
plus
show
1.
you.
And you,
Yes.
is that also?
Look, a short note about Thomas and Sammy. The rest don't care. They don't know how to solve the exercises. Okay, so I'll give you the long version first, but it will help you understand the shorthand version and why is it true. So I am winning it. And I'm saying, what is the basic win? We need 1 plus something, right? Because it's 1 plus n in the power of 1 over n. So it's 1 plus n over n plus 1 minus 1 to the power of n. Agreed? Now I'm continue to win it. No, I'm simplifying it now, sorry. What is n minus blah, blah? And so it's minus 1 over n plus 1 to the power of n. Agreed? Now again, I'm winning it. And I'm saying this is 1 plus minus 1 over plus minus 1 over n plus 1 in the power of its inverse minus n plus 1. Does that equal? 2 questions. Do you realize why did I go here?
No idea.
Because I want the complete inverse of that. Right? The rule was 1 plus an in the power of 1 over an. And you can say you've never seen it before, but you've seen it today. And then I scrolled up and showed you the scene before, but it's still the same rule that you are refusing to accept. There is a Hebrew meme, I'll tell you in short that there was a show with someone, they said she was a thief, convincing people she was blind and taking money even though they caught her seeing. And then she goes in the show and say, I'm not seeing, I'm telling you I'm seeing nothing. So it's a known meme. So every time I show students something, they say, we never saw it. We're not seeing nothing. I have no idea what you're talking about. Yes.
My feelings don't care about your logic.
Yes. Okay. So so again, the reason I didn't finish yet, right? Because this does not equal that. But what I wish to get here is 1 plus something that goes to 0 in the power of its inverse. Because that's like 1 plus 1 over n to the power of n. That goes to e. Okay, that's a theorem. But we need to fix it. How do we fix it? We divide, we multiply by the original thing and divide by what we added. Agreed? This.
In this case, can't you just multiply by -1 -1? Kind of.
No, because you have to have the exact inverse of what is there. So this goes to e. This is easy. What is the limit of that expression? -1. So the limit altogether is e to the power of -1. So without the trick I did, that will be like the way they expect you to do on the homework. And then I came up with the following shorthand. Look, assume an is different than 1, but tends to 1. And you have an to the power of bn. Is that the rule you were speaking about or not?
Yeah.
Okay. So we're winning it again. I'm doing the exact same thing. So for years and still now, in every university apart from Bar-Ilan and apart from my classes, the lecturers teach their student this way of thinking and expect them to do this each time from the start. And for me, this is like programming the same function over and over again instead once and calling it, right? It's the same operation. I do it once on a general expression, it will work. So I'm doing the same thing. First of all, I want 1 plus. So what will I have here? A -1. Agreed? But this is still not exactly what I need, because we need 1 plus something in the power of its inverse. Agreed that this is what we need? These are the wins. But again, this is not what we have. How can I correct it? I multiply but what I divided and by the original power that was there. And then whoa, what a weird break of line. Oh, weird. Okay, cool. And then finally we're saying this is 1 in the power of na. All of this in the power of an -1 bn. And everything in the square brackets, what is its limit?
One.
E.
Mhm.
Because that's 1 plus something that goes to 0 in the power of its
Okay.
inverse.
Yeah.
I've never seen that theorem in my life. Okay,
I never seen it.
I still did not. Okay. And this, let's just call this one L. I don't know. Well, let's leave it. And then the actual rule is that if an is different than 1 but tends to 1, then the limit of an, now he's taking a picture to say I never seen it.
Yeah,
I never even took a photograph
I'm
of
going
that.
to print it
That's
and
also
put it
yes.
on forehead.
So you will not see it on your forehead. That's not a good idea.
Is
Okay.
that the only issue you have with that idea?
Yes. Okay.
Uh,
So it's e
Zero.
to the limit of an minus 1 times bn. Why did you say it's 0? Wait. Why did you say it's 0?
Because the limit of an is 1.
Yes,
so 1 minus
perfect.
1 is 0, so 0 times bn is 0. So it's
0 times
the zero, which is
everything
one.
is 0. This is like you
okay.
cut calculus so short. Who needs limit?
Okay.
Limit 0 times everything is 0. No. Because the bn itself is usually infinity, right? It's 1 in the power of infinity. So here you get a 0 times infinity. But it's better than power. You get product instead of power. You can do a lot more things with it. So it's a much better situation. Okay? So that's the shorthand rule. So you can choose. I prefer the shorthand rule, but I'm biased. But you can do the long version each problem from the start, or use the shorthand rule, which basically means I did it once for you guys and you can use it.
yeah, I've never seen this actually. Anyway,
Yes.
if this is for all an tends to 1 and bn doesn't have to tend to anything in particular.
Yes, but usually if bn doesn't tend to infinity, it doesn't. If n tends to 1 and bn tends to 5, then 1 to the power of 5 is 1. You don't use it. You usually use it when bn is infinity. But you can also do it when bn is minus infinity, and you can also do it when bn switches between plus and minus infinity. So the beauty of it, yeah, the only assumption you need is that an tends to 1. And that's enough. And by the way, also when I say different than 1, it's because I'm dividing. Otherwise, I will be dividing by 0. But if an actually equals 1, then 1 in the power of bn also equals 1. It's not an interesting case. It's only interesting when an tends to 1 and it's not 1, and the power is unbounded, basically. Then when it's get interesting.
This is times bn, not divided by bn, right?
Times, yeah. The proof is here.
Why is it only when an is tending to 1?
Because here we use that this is 0. Because the rule is 1 plus 0 in the power of the inverse of the 0, which is infinity or minus infinity. Then we have the rule about the e. Okay, the one that Thomas did not see it.
Ever in my life.
Yes. I'll go back to it. Where was it? I'm
when
not
you-
seeing it myself.
That's not
Here, they remember that. Yeah. Here you need that this part goes to 0 for that to work. Think if an supposed is, for instance, was 1. 1 plus 1 is 2. In the power of 1, it's not e, right? It only fits when it's 1 plus something that goes to 0. Okay. It's for 1 in the power of infinity. It's different ways to write 1 in the power of infinity, basically. Any questions so far? So next, the 5th and final Spock test. The condensation test. I will start by writing it and then explaining it. And finally, I'll decide if I'll do a foolproof or stick with the explanation. I think already, I think I will stick with the explanation. And again, because the explanation shows almost everything, but skips just some finer, non-interesting details. So it goes like this. Assume AN is a positive decreasing sequence. This is important. In any of the first 4 tests, we just claimed positive. In the condensation test, we need positive decreasing. Agreed? Then, this is the only assumption. So it's a new assumption, but it's the only one. So that's nice. The following series are BFFs, meaning they either both converge or both diverge. So the first series is the original sigma of AN. And the second one is, hold on tight, 2 to the power of n times A in the index 2 to the power of n.
So something to differentiate.
That's a very good observation, Sami. What does this remind you of?
It reminds me of differentiating.
No differentiation. Well, depends on which. Not
integrate.
exactly.
Something like
It's integration.
integrate. Yeah.
Yes, that's what I meant.
It was. I knew it's either differentiation or integration of.
And you're in
X to the
calculus,
A,
and
or X to the-
you're in a calculus course, right? No,
Yes, you have some.
what is the integration of e to the x times f of e to the x? That's f of e to the x, right?
Of course.
No, this is similar to, and like I told you, the 5th test, if the students have learned integrals first, they don't do the condensation test, they do the integral test, which is much more powerful. This is a specific example of the integral test. We do it because we don't have integrals yet. Okay, that's the main thing. And why is it true? Do you know how to derive a composition of functions? You derive the outer function and you multiply it by the internal derivative, and you get to this. More concise language would be clearer to the reader, like it actually says that similar to is grammatically incorrect
Inferior.
because I should have written
No, that isn't.
like.
That isn't a that isn't a grammar check.
Can you open the options for conciseness?
No, it says like.
No, no,
Yeah, you have
Yeah,
options.
that's that. It's here.
No.
You
It's
have
that,
options.
it's
You
that.
can lower like the
Lower.
conciseness limitations.
Lower.
Option for
Yes.
conciseness.
Zero
Nominalization.
conciseness.
This is why I don't learn linguistics.
Ac bias.
H
Age bias. Inclusiveness. What?
What?
This is just, let's throw some progressive agenda on you.
Hey,
With no.
you didn't put on the
Ethnic
H
bias.
bias.
Racial
Ethnic
bias.
bias.
Put the H bias. Maybe let's get to Sigma mindset in the middle of the.
How much is that?
No, it's not I think it's grammar settings. That's what
You
happens.
have to write skibbity whenever.
So
Skibidi calculus.
but skibidi, it's so concise. This is skibidi. Yes, okay.
Just peep, mama.
Yes. It was options for conciseness.
Don't press that button ever again.
Don't check for this issue for the love of God.
Next day mesh.
No, but I think, but it gives us all options. And yes, there are
Formality,
some options.
inclusiveness.
Yeah, that's not certain. It could make the lesson more interesting.
What did you learn in P today?
Age bias, I love that.
You-
Age bias is simply children are stupid. That's not age bias. That's true. And it's not even biased because we were children as well.
You didn't put the datem integral.
Can we see how many errors popped up now?
Yes.
Or is it, has it not
Yes.
processed yet? There's too many.
Stupid people bias. You're right. You're for that. It's not fair. Okay, that was funny. No, but I can't believe it was similar to like dumbing down the next generation. Okay,
You think the next generation uses words?
yeah, words or word, yeah. Okay, so let's do a quick example before starting the explanation. Example. Look at the series 1 over n times log of n. It's an interesting example because it's smaller than 1 over n, but 1 over n goes to infinity. So being smaller than infinity is not helpful at all. And it's also interesting, and that I won't show, it's larger than every other P series. I'll teach you that notion later, that converge. So it's bigger than all the converging theories and smaller than all the divergent elementary series. So we don't know what to do about it. But we do know what to do about it, the condensation test. Since 1 over n times log n is decreasing, how do I know it's decreasing?
Log angles.
That doesn't mean increasing, that means tends to 0. Because the denominator,
Bigger than.
numerator and denominator. It's with I.
Yeah.
It's offensive
Yeah.
for, yeah.
It's offensive for people who don't know English.
It's stupid, like, give me some,
Gender offensive.
yes, give me some gender offensive,
1990.
stupid like a boy.
Like 1800s.
Stupid like a girl. That's not offensive. That's not
Wait, here,
offensive.
press enter, press enter.
It's not offensive.
Maybe you have to carry on writing.
Maybe I should have written stupid like a girl. Then, that's not offensive. Okay, okay. No, I really wish that it would find stupid like a girl offensive and stupid like a boy is not offensive.
Yeah.
But it finds none of this
Gender
offensive.
inclusivity.
Okay, okay.
I like the fact that this is recorded.
No one would believe me otherwise.
The denominator, the actual theorem was increasing. That's not stupid. Like, okay, the denominator is increasing, n is increasing, log is increasing. So if the denominator is increasing, the whole fraction is decreasing. So we need to make sure that in order to use the condensation test, and thus, this series, sorry, is the BFF of, yeah, but that's okay. And no one cares about that. No, by definition, we were friends, it wasn't offensive. Just stating a fact. Okay, so seriously, this is the important part, so try to focus. what do I do? Who is the BFF? I take the original series and then I do two things. I always multiply by 2 to the power of n. You don't need to think about it. And the thing which is a bit more confusing, I take the original sequence, but instead of n, I'm putting 2 to the power of n. It's actually a subsequence. Okay. So everywhere where n is written, I write 2 to the power of n. Agreed? That's what the test says. I didn't show you yet why is it true. It's actually quite nice and has to do with condensation. But for now, I'm just
Like
showing you.
water.
Yes. Yes. Like it's fumes of water. You say fumes of water?
Water vapor.
Well,
Vapor, yeah, I think vapor. Because in Hebrew, say
Edim.
edim. No, it's
Yeah.
vapor. Yeah, you vapor. That's the word, right? And okay, it's really like vapor of water, and the condensation is when a lot of vapor becomes a drop. It's really the proof of the theorem is really like that. You will see. Okay. In any case, let's work with this series here. What can you say about this series? What happens to the 2 to the power of n?
So
It cancels out. What can you do with log 2 to the power of n?
multiply log 2 by n.
N times log of 2. You can take log of 2 out. And what are we left with? The harmonic, yeah, the harmonic series, which is diverge. This is the diverging harmonic series.
Oh,
Of
no,
course.
no. This was in the. Have you seen the video about the approximation algorithm from Quake?
Oh,
I think that's like exactly the thing that they showed, where it basically could approximate.
maybe.
I have no idea.
What's Quake?
You're just too
Oh.
behind in this conversation. We'll talk later.
It's like the first 3D engine, good 3D engine for a game.
Yeah.
That was used for all the games, and has some interesting math behind
The
it.
game
I
is
read-
called Quake.
What?
Yeah.
The game and the engine is
Yeah,
called Quake.
Quake 3 Arena, something like that. And they have what's a good game? Okay. And this is the diverging harmonic series, and therefore our series diverge as well. Explanation. Explanation, no.
Explanation.
Was 2 A's. Explanation of the theorem. It is the main thing. I just skip details. Look, the original series is A1 plus A2 plus A3 and so forth. Agreed?
Okay.
I would like to enlarge it and to decrease it and do a comparison by two different series. And I'll do it like this. I'll add some more. 6, 7, 8 plus. Okay. So first of all, let's increase it. First of all, let's increase it. So how do we increase it? We need to remember that AN is decreasing. So by replacing elements by elements before, we're increasing. So A1, I'll leave A1. But both A2 and A3, I will switch by A3. So if I replace A3 by A2, I did an incretion. I increased, right? I don't think that was a word. I increased. Do you agree?
If it's decreasing, you increase.
Yeah, AN is decreasing, so A3 is smaller than A2. Who can guess what the next element would be?
A2.
A1.
Fine.
A4.
Yeah.
And then
And A4.
A4. And then
A6.
and then
A4 again.
A4. The next one.
A6
A8.
and 6
A8.
times.
Yeah.
A8.
What?
These are the fumes, the vapor. These are the vapor.
The mathematician breathed in when he came up with this.
These are the vapor. And oops, I should have marked the first A4. And by multiplying it, I condense it. So what happens? I threw away a lot of elements. One might think that will affect the series, but because the sequence is decreasing, whatever I threw is stuck between the elements I left, between the vapors I left. And if you notice well, what is the series we got here? We got A1, which is rather not interesting, plus 2 times A2, plus 4 times A4, plus 8 times A8, and so forth, which is A1 plus the sum from n equals 1 to infinity of 2 to the n, a to the power 2 to the n.
A1.
No. If I took 0 in, to be honest. Yeah, I usually don't do it, but it doesn't really matter because it's all about convergence. So what we've seen here is that our series, and it's really not far away from a full proof, right? I just need to get rid of the dots and speak about the partial sum sequence, right? I think that's enough to understand the idea. Yes, Sammy.
So what does this have to do with condensation?
Because the fumes are taking only the subsequence in powers of n, A2, A4, and A8. They are
When you say
all
fumes, what?
vapor.
No,
It's the
what do you
vapor
what
of
do
the
you-
series.
Essence, the essence, basically. You know?
It's like your meta. It's a metaphor.
Yes.
It's
It's not
not-
literally
It doesn't actually have anything to do with condensation.
Literally
then.
working on
it's a metaphor, obviously.
Wait, what's
I think
the
like
And the
is this like a way of
condensation is the
calculating, like,
multiplication.
the amount of steam you get.
Wait,
like,
wait,
I don't know.
wait. What's
No,
the-
it's a metaphor.
What's the benefit of this now? That's, I think it's not.
You saw how we solve it. I did before. You saw how we solved
No,
a
whoever-
question using it.
Whoever figured this out clearly wasn't a physicist or a chemist.
No, it's mathematics.
He was high on something else, probably fumes.
Yes, your iron fume. Okay.
Yes.
On the other hand, we wish to decrease. We'll decrease the original series. We will decrease as follows. So A1, I leave it A1. A2 and A3, no, sorry. I remember now. A1 and A2, I make A2 plus A2 plus A3 all the way up to A. No, let me make sure I'm not mistaken. It should be, no, I'm definitely mistaken. A1 is A2. Sorry. A1, I switch with A2. A2, A3,
Yes, with A4.
A2 and A3, I make A4. Then the next four elements, which are A4, 5, 6, 7, 7, yes, one before. These are also the kind of thing we need to prove that the amounts of element I take always step where I expect them to step. And when I expect them to end, sorry, A8, and so forth. So that is decreasing because I replaced each element by a small one because the n is decreasing, and we get here 1 time A2 plus 2 times A4 plus 4 times A8 and so forth. This would be suboptimal because we wanted 8 times A8, but that's just half of 2A2 plus 4A4 plus 8A8 and so forth. So our series is larger. So if our series converge, so does this one, it's BFF. And we prove both direction. Before we've seen that this, because half of it is converging, then obviously it's converged as well. So that's the main thing without all the details, but that's the main idea. And the idea of the vapor and condensation is that we take few elements and condense them into a drop. And because AN is decreasing, sorry, then it works. We finish with the 5 test of Spock. The next test will be about a general series when there could be both negative and positive elements. Yes, Thomas.
What you were trying to say here is that we can use this because doing it to the n is larger than our original series.
It's not, but it's not just 2 to the n. Taking elements every now and again and multiply. Taking just the elements, that's the vapor, and the condensation is multiplying it.
Yeah.
It's you can't say it in one word. That's what I'm trying to say.
Yeah.
But I've proved that this creates a series which is both larger and smaller when you divide it by half, and therefore it's a BFF. They are both converging or both diverging.
Sure.
Okay, that's the main trick behind this beautiful proof. But the use of it is like this. Okay.
This is only useful for cases that we have usually like n.
No, the next time it's a good note. Lecture 13 is the next one. Start with P series or harmonic series. Generalized harmonic series. Generalized harmonic series. Okay, okay. So this the main reason for the 5th test is this example that we will start with next time. Good day. That's a nice test.
XM will be, will be.
Can I just think